what I can do here is go ahead and run this. This will run that. And that took about 1 minute and 42 seconds to process all 213 million different polygons that exist in the Overture Maps dataset. So that's where the power of this comes in, where it's extremely parallel. Once again, all this data that from the raster data stays on AWS. I'm not pulling that into memory. I can just read it remotely. I'm only materializing the pixels that I need from the query. So you can actually do that in overlap those two here. And so that makes that highly efficient as well. And then the last bit is that I already have that data set existing in my Wherobots DB or Apache Iceberg. So those tables are basically just blank references that I have, and I can run that and update that as many times as I want. So, and the other thing is that if that raster data set does update, that makes it really efficient to be able to, change or update that, or if that changes at any time, I can certainly do that very efficiently. So that's another key process that happens here. So this will run the first time around. It took like 1 minute 42, should be about the same this time around to process all that data. We'll wait around and see. And it was 1 minute 15 this time, so it was a little bit faster. So that's kind of the whole thing, right? It's nothing too crazy or groundbreaking in terms of like what we're doing. It's it's a few lines of code here. And what's nice is like this Sedona plus Wherobots makes it so simple to just go out and do these things. Like I don't have to loop over a stack catalog JSON endpoint. I can just see where the files are and then immediately turn all of those files into a single data frame, which is highly efficient. I can also turn that and save that round into a table on Apache Iceberg, which is just cloud storage at the end of the day. So it's highly efficient to do that as well. I have my isochrones data here, which is already set up, or if I wanted to do a pure radius or anything like that, I can do that as well. But that's all set up and going from there. So, and then finally, it's just fast at the end of the day. It just works very quickly. I can run this. Once it's done, it's done. I can shut down my runtime, and it's easy to go from there. So it's just all these little efficiencies that make it really nice. Plus, this is all open code, right? You could take this exact code structure with Sedona. If you wanted to move it into a different platform, you can certainly do that. But Wherobots, the nice thing about it is it creates the very scalable runtime to run these very highly difficult spatial operations on, and does it with the open table formats and all these different things. So this was probably the fastest one we've done. But it takes this highly complex process, highly compute dependent process, and makes it really, really efficient. So that's kind of what we wanted to show you today, is how to do that with very high efficiency. You can take this notebook and modify it out. So any stack catalog that you find, I would recommend checking out AWS Earth. It's like where they store a lot of their Earth observation data. So you can see here, they can go to geospatial data sets. So you could do something like this with Landsat data if you wanted to. Anything that has like a stack catalog endpoint, and a lot of them do. If you go here, you can see that they have a stack endpoint here. This one's in XML, so that makes it a little bit tricky. Let's go back here. But you could do the same thing with like Landsat. They have a stack catalog. You could pull that data in. You can pass those in, and you could pass in any geometry file that you want, and you could just simply turn that geometry file and run the same code and structure, and you'd be doing the exact same thing, which is really, really nice. So I saw there's one question here. So I might have missed it, but when you overlap a vector and raster here with the zonal stats, does it make sure the projections match? It will error out if the projections